Good day, ladies and gentlemen. Today we're going to talk a little bit about ideal gases and their thermal properties. Now, you are all obviously aware that you have a solid, a liquid, and a gas, and that there are certain differences between these, how the molecules are arranged, the kinetic energy of said molecules, and one of the important things for gases is if they are heated, they tend to expand. Now, this is important a little bit later, but let's first look at the concept of an ideal gas. Now, because the motion of gases and the way gases behave is a relatively complex thing, we try to make life a little bit simpler for ourselves. So we use ideal gases to describe these things. And ideal gases have a certain set of characteristics. The first of characteristics is that all the particles are identical. So the entire gas is identical. All the particles are in constant motion. And then also the volume increases as the temperature increases, which of course, like I said earlier, if you heat the gas up, the volume increases, it expands. Ideal gases, we also assume, have no intermolecular forces. The speed of the particles is based on temperature. Not all the particles move at the exact same speed. So we use an average speed for the particles based on the temperature of the gas. This links to the theory that the temperature of the gas, the energy you put into a gas or any substance, influences the kinetic energy of said particles. So the warmer the gas would be, the more energy those particles have, the quicker the particles can move around. The pressure of a gas is caused by collision of these particles. So the pressure that you have in a container containing gas is as a result of these particles bouncing around and causing collisions with the sides of the container. You also have collision between the particles, of course, and we see those as being elastic. That is to say, no energy is lost when the two particles hit each other. That is fairly obviously not true, because collisions in general tend to not be elastic. You lose energy as sound, as light, as heat, as many things. Collisions just are not elastic. And then finally, in an ideal gas, we say that the rate of diffusion is high. Now, you might remember from previous work that diffusion is the movement from a high to a low concentration. So the idea here is that if you have a gas and something is introduced, that thing that was introduced will spread out through the entire gas, and the gas body will be the same. It is, in essence, we are trying to get the gas body to be as constant as possible, to have as few factors making our lives difficult as we can. We do not take into account intermolecular force. We say all the collisions are elastic. We do not want to make our lives difficult. Now, what is important to note here is that the collision and the pressure idea. So as we increase the temperature, we are going to have the volume going up, not so. this increase in volume is going to result in an increase of pressure. What that in essence means is that more collisions are taking place, because remember, pressure is caused by the collisions. So this temperature is increasing the kinetic energy of the gas particles, causing them to move around more volume, more pressure, because more collisions. Now, real gases then of course are, well, the real gases that we encounter in everyday life. Certain gases like helium, for instance, are very, very close in behavior to an ideal gas. The largest difference, I will say, between a real and an ideal gas is that a real gas, the particles actually occupy space. Now, this is very important because if you have a certain amount of gas and you put a lot of pressure on that gas, you make the container it's in smaller and smaller and smaller and smaller, eventually you're going to run out of space. That gas is then going to switch over to a liquid. I mean, you all know that you have solids, liquids, gases, and that gases can go from gas to a liquid. And that's what happens if you put a whole lot of pressure on a gas. Any of you who are perhaps geology or geography fans, you can search for something called a black smoker or a mid-ocean vent or something along those lines. These are in essence little miniature volcanoes that spew out water at a few hundred degrees Celsius, having been heated up by the magma inside the earth. Now, the reason this water, at a few hundred degrees, it should be boiling and going to gas, but because it's at the bottom of the ocean, all of that pressure is actually keeping it a liquid. It simply does not have space to expand. And then, of course, the other important thing for a real gases is that they actually have intermolecular forces. These collisions in ideal gases, we describe them as being in a straight line. The particles move in straight lines until they collide with the side of the container or another particle, and then they continue moving in a straight line. In real gases, that tends to not be the case, because you might have polar molecules with a slight positive or a negative charge. These will either be attracting or repulsing each other, which means that they might not be moving in perfectly straight lines. But again, if you have millions upon millions of gas molecules moving around in the container, exactly how do you accurately calculate that? So to make our lives easier, we just use ideal gases. And then, of course, luckily for us, some gases actually do behave quite close to these ideal gases. Now, of course, this is where things get a little bit more complex, because we can't just say temperature does this and pressure does that. We need to have quantifiable, repeatable, measurable ways of doing this. And the first person to do this was a gentleman called Boyle. And if my history actually serves me correctly, this Boyle gentleman did these experiments in the 17th century. Robert Boyle. I forget what nationality he was right now. Irish, I think, if I remember correctly, but don't quote me on that. Now, the easiest way to describe Boyle's law is to say it involves pressure and volume. Now, as we already said, there is a relationship between pressure and volume, because as the volume of the gas is going to increase, the pressure it exerts on the container is going to also increase. So what we can say is that the volume and pressure are proportional to one another. If we were to graph that, it would look something like that, with pressure and volume. Now, a graph looking like this, that makes math difficult. So what we do is we say they are inversely related to each other. If we then were to say pressure and 1 over volume, then the graph looks like that. And that makes the math a whole lot easier for us. Because remember, we don't want to make our lives more difficult than it needs to be. So we say volume is proportional to pressure. But we don't want to use it like that. So Boyle's law is that volume is inversely proportional to pressure. And we write that as such. Now, some people don't like these graphs and math and stuff like that. So Boyle's law in sentence form, in words, would be that the volume of a fixed amount of gas, and remember we say a fixed amount of gas because we want to have as many things constant as we can. Okay, so a fixed amount of gas is inversely proportional to the pressure on the gas. If, and again because I want to keep things simple, if the temperature is constant. Now, this in and of itself might not really help you that much to understand what's going on. But the crux of the matter is that if we have a temperature, and temperature does not change, and if we have a volume, an amount of gas, then the amount doesn't change. So the only things that then change is the pressure and the volume. So we can do some mathemagic, and we can take Boyle's law and we can convert it to say that if temperature equals constant and if the amount of gas equals constant, then the pressure times the volume of a gas at a certain instance is going to be equal to the pressure and the volume of that gas at a second instance. And I find that the best way to do this is to sort of do a little example. So let's say that we have an enclosed gas. Let's just write our formula here. We have an enclosed gas, and we are looking at the relationship of the volume and the pressure. And we've got a little graph, let's say. And here we go. On this axis we have pressure in kilopascals, and over here we have 1 over volume in meter cubed. And we have two gases. We have gas A and we have gas B. Now, this is the relationship of pressure and volume over time. So let's say for gas A, we have 2 points. We have this point where the pressure is 150, and we have this point where the pressure is 100. At the 100 pressure point, its volume is 5.0, and at this one, we don't actually know what its volume is. Now, because this is a gas, that we assume the volume or the amount of gas particles, we should not be using amount and volume interchangeably. the amount of gas is constant and temperature is constant, we can then use our formula. But, of course, there's a trick. There is always a trick. Remember at the very beginning when I said that we have inverse proportions. Okay? Now, let's start. Let's say we have P1, we have V1, and let's make that these two. So our pressure 1 is equal to 100, our volume 1 is equal to 5. I assume you would agree with me. We then have our pressure 2, which is going to be 150, and our volume 2, which is an unknown. So if we take our formula, P1 V1 equal to P2 V2, V2 is what we want. So we can rearrange our formula to get V2 is equal to P1 V1 over P2. Or you can write it as a linear equation and write that out. In the end, it doesn't really matter. So long as you obviously get the correct answer. How you choose to manipulate your formula, it is actually irrelevant. But here comes the trick. You see the formula uses V, but you see our graph gives us 1 over V. That's a problem, because our formula does not use 1 over V. Our formula uses V. So we need to change this. So this right here is wrong. 1 over V is equal to 5. That means V is equal to 1 over 5 if we switch it around a little bit, and that is equal to 0.2. So this right here should be 0.2. And I deliberately made that little mistake to do it this way, because this is what 99% of people do. They do not take this 1 over V and change it to V. And that's where most of the mistake comes in. This is a linear formula with one unknown. The odds of making a mistake there, even if you manipulate the formula, relatively small. Most people struggle with these and get the wrong answer because of this. Because they assume that this is V, which is what the formula uses, and not 1 over V. But we now have 1 over V, which means we can now continue on our merry way. So we can use our manipulated formula, and we can say that thing equals P1, 100, V1, 0.2, because remember V, not 1 over V. And then we have 150. And of course, this 100 and 150 are pressure units. So the only thing that's left is our volume unit. So we're going to have a volume, obviously. And if you work this out, you get 0.13 cube. There we go. So what happened was the pressure, let's just write that there. I'm just going to change my graph a little bit to illustrate the answer. 0.2, 0.13. So the volume decreased. That means the pressure increased, because as the volume went down, the pressure increased, because obviously 150 is higher than 100. Now, most people, I've noticed, tend to actually stop caring about any explanation. They just want the answer. And if you happen to be one of those people, just please remember to use the right units in your formula. Now, Boyle's law is the first one that we have looked at. And the next one we are going to look at is going to be Charles's law. Now, Charles's law is the second one, and there are actually about 4 or 5 others. So I think, because we've already had such a nice long discussion on ideal gases and such, that we will do Charles's law and the others in a separate video. So until next time, ladies and gentlemen, have a nice day.